Hello, this is Mr. Mitchell. We have had instruction on how to name chemical bonds. You may remember we had rules for ionic bonds and rules for covalent bonds. Well, there are some special cases that I want to devote this video to. Naming compounds in special cases. Well, one of those special cases is transition metals. The transition metals, you may remember, are these that are in blue on this particular periodic table. They're the ones that we have not been setting a valence for. You may remember these columns that I have the pluses and minuses above. They're the easy ones. You just see what column they're in, and they're always going to have the same valence number, the same number of electrons in its outer shell. But that's not the case with these transition metals. Something like copper, which is Cu, sometimes lends out 1 electron, sometimes it lends out 2, sometimes it lends out 3, and that's what makes these a special case. So what are we going to do if we happen to have a compound that has one of these transition metals in it? Well, the first thing to remember is that in essence it's still ionic. You may remember ionic has 1 metal and 1 non-metal. So all of these that has a transition metal in it is going to be linked with one that is a non-metal over to the right side here. So keep in mind you'll have the same rules for the most part as ionic. You name the metal first, and the whole compound ends in IDE. But you have to use the other element in the compound to tell you the transition metal's valence. And it's going to look like this. You see it has copper 2 fluoride. The 2 is going to be the metal's valence, and it's always going to be plus. So this is like saying copper is plus 2, and fluorine, you look on the chart and see that it is -1. And from there, you could tell you would need more fluorines. But anyway, let's take a look at MnO2. Mn is manganese, and manganese is one of those transition metals. So we don't know what the valence is by looking in its column like you typically do with the others. So what does it say to do? You have to use the other element to tell you its valence. So the other element in this case is oxygen. Oxygen is a -2. You see it's in this column here that says -2, but there are 2 of them. So you have -2 and -4, my bad, -2 and -2, and that makes -4. So manganese has to make it equal 0 and has to be +4. So I don't have my tablet with me, so if I were to write it out, well, I would write manganese in parentheses 4 oxide. Because keep in mind, it's ionic, metal first, ends in ID, manganese oxide, except between them you would put 4 in parentheses. So if we were to go backwards, and let's say you were given the formula, copper 2 fluoride, you still have to use the other element to figure out what the formula would be. So we mentioned that copper here is +2 because it says it's 2, and fluoride is -1. So in this case, you will indeed have to have more than 1 fluoride. I think I can still write this one out, even though I would have had a hard time with the other. So copper was +2. That doesn't mean you give it a subscript of 2. That just means that its valence is 2. And fluorine is here, and it was -1, so you will need 2 fluorines to even it out. So copper is +2, and you have -1 and -1 if you have 2 of them, and that's what's going to end up being your formula. CuF2. And down at the bottom, it was manganese 4 oxide. There's another special instance. Polyatomic ions. Polyatomic ions, well, we have a common list of them here. These are elements that have already bonded together. However, they have a charge, which means that they're going to still try to bond with other things. So when they do bond with other things, you sometimes have very long formulas, but fortunately there are lists of common polyatomic ions. Now here's some things to remember. You don't use any prefixes on any of these polyatomic ions like you would with covalent bonds. We're not going to have dinitrogen trisulfides and stuff like that. It already has its name. So you're going to use the name of the other element and this. And you would treat these like any other element. Now I know, for example, this acetate has 2 carbons, 3 hydrogens, 2 oxygens, but you treat it as a C2H3O2. Treat it as one thing, and that one thing will have a charge. In this case, it's going to be negative, which is -1. So let's take a look at an example. Here we have calcium nitrate. Calcium is on the periodic table. It is Ca, and it's going to have a charge of +2. But let's see what nitrate is. Okay, here is nitrate. Nitrate is NO3, and it has a charge of -1. So treat this just like you would treat a regular element. It's an NO3. So if we were to write the formula for this, calcium is Ca, and we know that nitrate is going to be NO3. It's just a matter of where do we put any additional subscript. So if NO3 is -1, as it says here, and calcium is +2, then we're going to need 2 NO3s. So the way you do that is, since you're treating it just like one thing, you're going to put parentheses around it, and then you have 2 NO3s is how you would go about that. So calcium nitrate has the formula CaNO3 2. Let's go backwards. Let's say we have the formula and we want to find out what it is. That's a little bit easier. You do not have to use any parentheses as far as valence for this. This is treated just like another ionic compound. So you have sodium, which is Na, and you have CO3. Let's see what CO3 is. Carbonate, right here. So in this case, the valences, the signs -2 and +1 for Na, they've already been used. So you don't have to worry about making anything different outside of just naming it sodium carbonate. So I don't have my tablet with me, so it'd take me a long time to write that out, but it's just sodium carbonate. You do not have anything in parentheses there, and the only time you'd use parentheses with polyatomic ions is in case like this. So hopefully you can use these as a reference whenever you're practicing these in class or at home. Thank you.